Good morning, everyone. Thanks a lot for coming to my talk. I'm really excited to take you all to the journey of fleet telematics using computer vision. But before we start, I would like you all to watch this video for a moment.
Today in Eau Claire. In the slowdown recording, you can see the car cross a grass median and slam into another car that was waiting at a stoplight. Both cars flipped into a parking lot. Police say that the driver was drunk at 9:30 in the morning. Today in Eau Claire. In the slowdown recording, you can see the car cross.
Each year in the United States, we have around 6 million crashes on our road. That is 37,000 lives lost, many families shattered, billions of dollars of property damages. What if we could change all that? What if we could revolutionize the driving behavior and reduce the accidents on our road? What if, imagine a world where technology works for justice, speeding up the process of insurance companies, aiding police investigations, and ensuring that the victims are not waited longer but compensated immediately. A world where those responsible for the accidents are held accountable and thus ensuring our driving is safer on our roads. Today, we're not just going to imagine that world, but discuss how to create it. And with not the use of expensive LiDARs or stereo cameras, but with very affordable small dash cams, which I guess almost all of you would have on your windshields. The dashcam industry has been growing exponentially over the last few years and is expected to grow more. Here, I present to you two videos showing the efficacy of dashcam video in capturing the unsafe driving on roads.
91 in Long Beach. The car that crashed was a blur going up to 90 miles per hour. The impact recorded on Tati's dash camera.
It was pretty bad. I mean, that area is pretty dark, so I didn't see much, but I did see the flames start. So I was just scared, and I didn't realize that anybody had,
Pretty brutal, right? In the first video, we noticed that the car was driving at 90 miles per hour. And in the second one, in order to take over the truck, the car goes in a wrong lane. Dashcams are definitely effective in capturing all these, but dashcams collect a lot of data, right? How do we process, how do we extract the useful and meaningful data out of them is what we will be seeing today. Now, before I dive into the heart of our talk, I would like to set the stage. First, I would be talking about the motivation of my talk today. What is it that we are trying to solve? Then I would talk how we are solving it. What is the AI-based methods behind it? Then I'll show you the scenario analytics tool we have and its importance. I'll discuss some challenges we faced while building it, and would love to take QAs at the end. And I'll also leave out my contact information if any of you would like to reach me out. Before we dive in, let's look at this video for a moment. And that was a crash. This video was extracted from one of our customers' collected data for over 64 million miles of the drive. How amazing would it be if we not only extracted this data, but also analyzed what was the speed the ego vehicle, the vehicle with the camera, was driving at, whether it was taking a right maneuver for the lane change, whether it had put a hard deceleration the moment it recognized another vehicle was there or not, right? Well, we have it. As you notice on the left side, we have the analysis of both the vehicles in the scene. And we also notice that the vehicle with the camera, the ego vehicle, was driving with perfectly calculated lane change, smoother way, whereas the other vehicle, the actor in the scene, took an abrupt change to the lane. More than that, we also have the information to describe what was the deceleration rate, what was the cruise rate and acceleration during the entire time. How do we do that will be what we will be exploring today, and more so. So let's describe how the entire system works. We have millions and billions of hours of data collected through our AV and ADAS vehicles, correct? That data gets stored in metadata, in database. Sure, but then how do we extract the data which our insurance companies would require to analyze what's happening? Or the police investigations would require what exactly happened during accident. There are a lot of useless data, but extracting the meaningful data is what our extraction engine does. Now that data gets used by reconstruction of the entire scenario, gets used by the product training and testing in-house for our engineers, get also used for giving the risk scoring for the drivers so that they know, the insurance companies would know what to charge them for. Various other applications are giving in-time driver behavior monitoring. That is, when the driver is driving, we can let them know that they're pressing too hard on the brake or they're pressing acceleration too hard. We can also reconstruct the accident for analyzing it later. Could be used by insurance companies again. As you can see, that was done in Carla simulator. We can also, as I discussed, extract the meaningful scenarios, like I mentioned, 64 plus million miles of data, and you can extract the snippet where an event actually happens. For example, a cut-in or a cut-out. We can also optimize the routes. If we have a lot of cars being stuck at one place, we would know they're stopped in that position for very long, and we can let the other vehicles take different routes that time. With all our scenarios, we can also optimize those routes. We also have real-time safety features. It's a little more futuristic, but it's not that far off, where we can have the forward collision control from our scenario and let the drivers know that they should put the brake, slow down the vehicles. Forward or backward collision control is pretty much on our way now, so not too far. Now, okay, so that was the motivation, right? Let's see how we do it using AI. So as I had described, for our entire data, for our entire pipeline, we do not require any expensive sensors. We do not need LiDARs or stereo cameras for finding out how far any other object in the scene are. All we need is Dashcam. And how? So how does a Dashcam, which is a camera, right, collects the 3D view of our world around us? That is through our simple and novel method, which we also presented at CVPR last year and is patented. The algorithm is pretty simple to understand. We have one backbone. We have two tasks: performing object detection of all the objects around the scene, and also finding how far they are from the ego vehicle, the depth prediction. We have one backbone and two heads, one for object detection, the other for depth prediction. Why are we having a shared backbone? That is to improve the accuracy so that whatever the object detector identifies, our depth network takes that region of bounding box, finds the median of all the pixels, the depth of all the pixels, and determines the depth of that particular object as the median of that. Now you must be asking, why median, why not mean? Answer is pretty simple. We have bounding boxes, which is not super tight. So it might have few pixels belonging to sky, and you all know what the depth of sky is. Well, our depth network would definitely not give infinite. It would have a cutoff at 80 meters or max, whatever. But that kind of corrupts our depth value for the object, right? For example, a truck might not be fully bounded. It might have few pixels belonging to different regions in the scene. And the depth, the mean, would get pulled away from that, will be affected by the outliers. So we take the median. Now, once to make the detections and depth prediction more robust, we also perform tracking and smoothing across multiple frames. So each frame is then passed back and done the object detection based taking the cues from the previous frame. So this tracking, this combination, the output of all of them is represented here. We have object detection plus depth prediction from the output. We then pass it to the object tracking and association or smoothing across the frames. And this is the output we get. Great. We also have lane segmentation network, which is to identify which lane any object is in. So what happens, how does this model work, is we take the photo of a road, right? We feed it to a semantic segmentation network, right? Any simple semantic segmentation network, and we get binary segmentation view. Now, what you see in the perspective view image there, the black and white, is a very smoothed out image, right? Obviously, like the binary segmentation, if it is only doing 1 and 0, it won't be that accurate. How are we getting that accurate? Accuracy is by applying some post-processing, that is connected components. Connected components and dilation morphology are traditional computer vision methods which says, okay, just connect all the ones in our image together. And once we have all the ones connected, dilation morphology says, okay, let's see which ones in the line might be missing from here and there. Then it tries to assign the values to those as well. Once we have the corrected binary segmentation network, we then project it to the bird's eye view. Now, what we have is the camera view, right? Camera or perspective view. We project it to the bird's eye view or top-down view. From there, we can segment each lane parallel to each other, because lanes in general are parallel. But in perspective view, they get converged. So in bird's eye view, we straighten them, make sure they're all parallel to each other, and then project them back to the perspective or camera view and onto the image. And so this is the video from one of our data to show you how it works. All right. So these are the two networks that we use, and you know how they are functioning, right? Now I'll show you the scenario analysis and extractor tool that helps any user extract the information. This is our scenario extraction tool by Ridecell called Nemo. It's pretty simple. How it just helps users to, instead of dealing with all that back-end stuff, all you have to do is just type in just go to the search. When you go to the search, there are many options there. They will ask you what kind of scenario you want to look for. Let's say you want to look for cut-in scenario happening with a bicycle. Or let's say you want a pedestrian walking by across the street. You can feed in all such information into our search type. For example, here we pass axle, and we pass cut-in from left. We then go for instant search, and from the millions or billions of miles of data, we get the extracted information. And if you right-click on that, you can zoom into each information. That is, what was the duration of the entire event? How was the ego vehicle performing? How was the other actor in the scene was performing? These are the pre-programmed scenarios, but we also have options for everyone to program them. For example, here you can take any of the templates mentioned and program your own scenario. You can say, okay, I don't want 2.5 seconds of cut-in. I want a cut-in where it happens, let's say, for 5 minutes, right? So you can do all of that programming. You can just take the template, change whatever you want, and you get the extracted data for your customized version. Moreover, you can also do more analysis. For example, in the right bottom side, we have collected data from different distributions, and you can see what were the distributions of each of the data. You can also see what were the scenario distributions across the data. It gives you a lot of freedom to work with it. Now, let's tie things together. You saw the AI, and you saw the tool. How did we get from AI to the tool? That is through our algorithm saying, okay, we have object detection depth prediction network, and we have lane segmentation network. The scenarios are built on top, saying, for cut-in, for example, in top, you can see, for cut-in, we can say, for any vehicle which has longitudinal depth, longitudinal distance from the main vehicle, ego vehicle, increasing over time, but the lateral distance decreasing. And we can put the threshold of that as the lane width, right? So if it is decreasing with the lane width, that means it is cutting into our lane. Similarly, for a cutout here, we have the algorithm saying for any of the vehicles in the scene, if we have the lateral distance increasing by the lane width, then call it a scenario, call it a cutout. These are the RSL queries, the Ridecell inbuilt query language that we then show. You don't have to worry about it. The moment you feed in the data, it automatically creates to extract it from the data. This is just to show you guys how it works behind the scene. All right, so pretty cool. Now we know the AI, we know the tool, we know the algorithm. We're ready to save the world, aren't we? But with any groundbreaking technology, things don't stop at innovation. Real challenges come when we go to the exploration or implementation of it. And I would like to discuss some of the real-world challenges we faced and their solutions, which might help you all too. So I might have said that we don't need dash cams at all. We don't need LiDARs for any of the networks, and that is true. We don't need any other sensors other than the dashcam 2D data. But during training for our depth network, we do require ground truth for the depth data. And depth data is only collected from LiDARs. So LiDAR have a cutout length of 80 meters, but cameras don't. So here we can see the small objects far away are still getting detected, but their depth are wrong, right? The simple solution for us was to cut off the 5%, any object smaller than 5% of the image size from our detection. Similarly, we have a lot of overlapping objects, which cause varying, as you can see in the right bottom, the object is more than 50% of the front object, right? The depth varies in this context and causes our scenario extractor to fail. In this case, we take the median only from the non-overlapping regions. We remove the regions which are intersection of all. Similarly, as I was showing this truck, the structure says that more than 50% of it belongs not to the truck, right? The depth of those regions vary a lot. Then what do we do of that? Similarly, as you can see, the right bottom, there's a gate with bars, and that consists of 50% of the object bounding box. The depth of that, again, the depth of the gate is very less than the car behind it. So the solution for all of that was to just remove the objects which are static in our case, right? Which we only want the objects which are actually the actors in the scene. For example, the one which are moving towards us or going away from us. So we tried using the triangulation method, the SFM, which just portrays one object to the other and sees which of the object moved. Just do the subtraction across the scene and find the objects which moved and take those or remove the static objects from the scene. Here it shows the moving objects. So to summarize, we have AI, machine learning algorithm, finding object detection and depth prediction. We also have lane segmentation network. We use algorithm to combine them. And we have the UI tool for users to use and extract millions of miles of data for whatever scenarios they want. Now, this task was not easy, and I would like to thank my teammates for this. Thank you all for coming to my talk. If any of you have questions, please feel free to connect with me. I'm available here.